Hi guys, this is the note video for topic 1.8, accuracy and precision. So one thing we strive for in any science, but especially in chemistry, is how to make measurements accurate. And so anytime you make a measurement, there is opportunity to produce error in your measurement. One way you can do that is using an inappropriate instrument. Like if you want to measure something with drops, we have an instrument called a burette. And you've probably used a graduated cylinder before in previous labs. And so if you wanted to measure the number of drops in regards to a volume, a burette would be a better piece of equipment to use over, say, a 1 liter graduated cylinder. The next thing is not using the instrument correctly. So if you're not aware of how to read something correct, then you're going to create error in your experiment. And then the last thing we strive for is to read an instrument all the way to its best potential. So for example, on a ruler, when you're measuring centimeters, a centimeter measurement can read to 2 decimal places because of the tick marks that are provided. And finally, you always have an estimated digit. And so there's different ways, again, that you can have error occur in your experiment. So today we're going to first start with how to calculate what's called percent error. And so these are some of the terminology that I'm going to use. So typically in a science lab, you have 2 types of data, quantitative or qualitative. Qualitative data is things that are descriptive. Quantitative is numerical measurements. So when you make numerical measurements, you can have what's called the experimental value. So that is what you calculate yourself in the lab. The accepted value is what you truly should have for an answer, and that's based on an agreement with the scientific community. So for example, the density of gold is 19.3 grams per cubic centimeter. That's the accepted value. Now you could take a gold ring, measure its mass and volume in the lab, and get your own density for gold. And what you can then do is calculate what's called the percent error, which is based on looking at how your value differs from what it truly should be. So unfortunately, I left my pen at the school, and so I'm not able to annotate on my screen. And so I've typed everything in, so I won't be working out the couple examples by hand, but I do have everything on the screen and I'm going to talk them out. So the first thing is, this is the formula for percent error. It is the experimental value minus the accepted value divided by the accepted value. Notice that it's got those brackets on each side. That's representing that you are going to find the absolute value. So again, absolute value from your math class is how far you are on a number line from 0. So you can never have a negative percent. And then the last thing is you times by 100. So here in the practice problem, it says that a student has a 25-gram calibration weight. Student A obtains 24.81 grams. Student B obtains 25.24 grams. In this example, the accepted value is the 25. So when the students are using the scale, it should display that that mass has 25 grams. What student A is getting from their scale is that it's 24.81 grams. And student B, their scale is telling them that it's 25.24. So what we're going to do is find the percent error for each using the experimental minus the accepted divided by the accepted times 100. So when you take a look at my work for student A, they have the accepted value is 24.81. I subtracted that from 25 divided by 25. When you put this through on your calculator, you're going to subtract, divide. You'll take the absolute value. So you want to simplify what's inside the absolute value first. This person's percent error is going to start out as negative because their mass is below or smaller than 25. So you take the absolute value of it. So again, turn that negative into a positive. The last thing then is you are going to times by 100. So I'm realizing now that, let me change my screen real quick. I put my zeros, I flipped things around. So let me fix that real quick. So this should be what our final answer is. But anyways, what I was getting at is that when you go to put this into your calculator, a lot of times students think they need to put the percent sign into their calculator. You do not. Percent sign is just like a unit. So when you subtract and divide things out, and with significant figures, our answer is 0.7600%. You're going to do the same process for student B. You're going to take their experimental value. Everything else stays the same because they're working with the same calibration weight. Running it through, this one is going to be a positive percent error because their mass is above what it should be. Again, when it's positive and on doing the absolute value, it's not going to impact it. You're going to times by 100. Again, percent does not go into your calculator. It's a unit. So you get 0.9600 with sig figs. It then asks who is more accurate, A or B. When it comes to percent error, you again are essentially comparing how close is your data to what it truly should be. In a perfect world, your percent error would be 0%, meaning your numbers do not differ at all from what it should have been. So student A has a lower percent error, therefore student A is more accurate. Again, the lower your percent error, the closer you are to the true accepted value. On the back side of the notes, or the second page, I really should say, this is another percent error formula, or a problem, I should say. And so we have a student working on finding the density of pure aluminum, and they found the density to be 2.85 grams per cubic centimeter. It says the accepted value is 2.699. What is their percent error? So I have the formula. Again, they found 2.85 as the experimental. 2.699 gets plugged in for the accepted. Again, you'll do the subtraction step here and divide. Take the absolute value, which this one will turn positive anyways, so you don't really need to do anything for that step, and multiply by 100. When you end, you get 5.59%. So the last thing that I want to discuss in this section is how accuracy and precision are not the same thing. So accuracy is what we just represented with our percent error formula. So the lower your percent error, the more accurate that you are. Precision, you can be precise but not accurate. And what I mean by that is, say you were that student using that scale and it should have been 25 grams. But every time you took a mass of, say, a penny, it told you the mass was 30 grams when it really should have been 25. So when you replicate something repeatedly, even though it's not the true answer, but you're able to replicate it each time, that is precision. So looking at these targets, it's asking, are they accurate or precise? So with this first target, we would not describe this person as being accurate because the goal is to hit the bullseye. However, we would describe them as precise. They have their shots grouped together. So again, they're not hitting the bullseye, but they replicate it and they have that grouping. The center target, we would say that they are accurate, they are hitting the bullseye, and they're also precise because they're hitting in the same region. It's very difficult to be accurate but not be precise. You kind of have to be one to be the other with that particular scenario. And the last one, where we have it all over the target, they are not accurate. Hitting the bullseye once does not make you accurate when your other 4 pieces of data do not. And it is not precise because it is not grouped well together. So the last thing then in this section is here is a data table. And reading the information, it tells us that the density of this cube should be 10.8 grams per milliliter. Is the data accurate, precise, both, or neither? So if you take a look, we have 3 trials, and they found the density of this cube to be 6.2, 6.3, and 6.5. So they are only precise. They are not accurate. Hitting the bullseye on the target would be that their data is approximately around that 10.8. Their data is nowhere near that 10.8, so they are not precise. However, their density is hitting the same region of the target, so it's grouped together, therefore it is precise. So your homework is going to be working on this section here. Just like with dimensional analysis, the expectation is you need to make sure that you show work with units and answer with unit, and make sure you round to the appropriate number of sig figs. Some of you are skipping those steps, and you're going to start to lose credit on your assignment by skipping those steps. Please let me know if you have any questions or concerns.